The next person in this kind of field we're looking into here started to make a little bit more sense of all this, and his name was Niels Bohr. And Bohr is incredibly cool. I really respect Bohr more and more as you talk about him. Bohr has an element named after him, borium, which is kind of a cool thing. But anyway, Bohr was a young aspiring scientist at the time, and he was trying to build just a simple model of the atom to figure out what was happening, because no one was totally sure what was happening. And where he came about doing this is he was looking at something called sharp line spectrum. So if you take atoms and you excite them electrically, you can actually make them have a sharp line spectrum. So in the lower right there, you can see here are some examples of some sharp line spectra. I want you to pay special attention to the first one, because that's the spectrum for hydrogen. And we're going to do a lab in Chemistry 221, which is going to look at the sharp line spectra of hydrogen. So you can see there's a couple of very, very sharp lines, very, very well-defined wavelengths. That's the sharp line spectrum. And how they got those is they took essentially like a hydrogen light bulb, if you will, a light bulb with hydrogen inside. They added a bunch of energy to it, so it started to get excited. And when they put it through a spectroscope, which is able to discern the different wavelengths, these wavelengths popped out, which is really cool. So instead of hydrogen being in the light bulb that you applied electricity to, if you, for example, used mercury, which is the next one down there, you can see you get a completely different spectrum, all right? More lines involved and stuff like that. And you might think, well, mercury has more protons than hydrogen, maybe that's it and stuff. Well, not necessarily, because the third one down is for neon. And neon has many fewer protons than mercury does, so it's something else is going on here to create this. But what's really cool about these sharp line spectra is they act as fingerprints for scientists. So these different elements have their own fingerprint when their spectra are excited like this. And you can identify them if they're in, say, a sun, many, many light years from the Earth, stuff like that. If you see these lines, then you know you've got those elements inside there. But at this time, they had no idea what was happening, and Niels Bohr decided to take a look at it.
If we pour methanol onto sodium chloride and ignite it, the flame produced is yellow in color. If instead of using sodium chloride we use boric acid, a compound made of boron, hydrogen, and oxygen, the flame produced is green in color. Each salt imparts a characteristic color. The emission of light by heated or burning objects provide important clues to our understanding of atoms.
In the real world, you don't need to have a special light bulb and excite it to see these things. You can actually see a lot of these colors just around us all the time. And the best example of this is if you've ever been around a campfire. Campfires are usually kind of a yellow-orange color. Well, that's sodium. The sodium is what creates that kind of yellow color around it. And in the lower video there, sodium is the third from the right. It's definitely kind of a yellow color. There's a lot of sodium around us all the time, which is kind of cool. On the other hand, you don't have to have those colors. So there you can have, for example, a boron, which is kind of a green, or potassium is kind of an orange and stuff like that. You can have all different colors, and this definitely leads to fireworks, which is one of the great examples. Neon gas can be excited to have different colors. You can have all different kind of variations from it. So yeah, there's a lot of uses of these excited gases outside of science.
If a high voltage is applied to an element in the gas phase, the element emits light. Using a prism, we can split the light into its component colors. Every element emits a distinct set of colors unique to that element.
Now, this video just showed what we're going to do in lab when we do the hydrogen spectrum lab. We're going to take like a fancy light bulb, which is made of hydrogen. We're going to add a lot of electricity to it, so it activates the light bulb. And then the light that comes out initially looks kind of blue, kind of red, purple, all right? Kind of looks like this light bulb does right here. But if you take that red, purple light and you put it through a prism, which is what's happening right there, then you end up seeing some very very discrete lines. This is the sharp line spectra for hydrogen. And hydrogen in the visible spectrum has more or less 4 lines, all right? So if you look on the left-hand side there, that end of the video, there's a red, there's kind of a yellow-green one. I don't know, the 486 one, people interpret it different, doesn't matter. And then there will be at least 2 purple lines. The 397 nanometer line is hard to see, so you probably won't see that. But there's usually at least 4 dominant lines in the spectrum, which is cool. And this is the fingerprint, if you will, for hydrogen. And again, if you put oxygen through there instead, you'd have a whole different set of lines visible that were showing up. And if you put mercury, as we saw the picture of earlier, you'd see something completely different. So pretty cool kind of stuff, these excited spectrum. This is hydrogen once again. We're going to see a lot of hydrogen here, but I just want to focus again how wavelengths are getting bigger as you go left to right. So you can see 397 is smaller than 410, et cetera, all the way up to the big wavelength at 656.3 nanometers. But as wavelength gets bigger, that means the frequency is getting smaller. So on the right-hand side, we'd have the smallest frequency or the lowest frequency, and the left side, we'd have the highest frequency. And finally, because frequency and energy are proportional, that means that the red light would have the lowest energy, and the wavelengths on the left, the purples and stuff like blues, they would have the highest energy, which is really cool. So Balmer was a scientist who was the first one to discover these lines, and he was the one that kind of first thought about it, and he measured them and stuff like that. Balmer didn't understand where the lines were coming from, but he at least saw that they were there. Now, remembering that, again, all these different ions, if you excite them, they start creating light. If you apply electricity to a pickle, which is just kind of crazy, I know. But anyway, pickles are usually soaked in sodium chloride, like brine and stuff like that. And it's the sodium inside that starts to excite. You can actually see them have kind of a yellow color like that, which is pretty crazy. I had a student once who was really interested in this, and he first of all did a regular pickle, saw the yellow, but then he soaked it in potassium chloride, and it actually had kind of a darker orange kind of a color. It was really, really cool. So anyway, lots of uses of these things. These sharp line spectra are super cool. And again, you can identify one atom from the next, which is pretty fantastic. So this is a question you might see. It says barium emits a green flame, and the question is what color should be observed in if you did an electric pickle soaked in barium chloride. And you could have a pickle soaked in barium chloride. I wouldn't want to eat it, but that's okay. Well, anyway, if barium has a green flame and you apply electricity to it, then the barium chloride pickle should be green as well. So it's the barium, the metal here, which is responsible for the color. It's yellow if it's sodium, kind of an orange color if it's potassium, and barium would certainly be kind of a green color. So now here comes Bohr, all right? And one view of how atoms were arranged is that electrons would travel around the nucleus. They knew the nucleus was positive and electrons were negative. They thought that maybe electrons would travel around the nucleus like planets around the sun. So they used ideas of electron orbits to describe how the electrons went around. And that was a popular theory, because if the planets do it, why don't the electrons do it around atoms? So the problems, though, became apparent pretty soon, because in theory, you could have any orbit around the nucleus. So you could have, for example, the electrons where they are right here. You could have them right here, but you could also have them like right there or right there. They could be anywhere around there in theory, all right? That's not what people generally saw. But the other thing that was more important is that as electrons, which are negative, start circling something positive, you begin to get into friction. And friction is when you create energy from things rubbing against each other, and eventually it's going to emit some energy. So if that happens, there's nothing good can happen. The electron would probably go flying off away from the nucleus. The atom would break up. So you can't get a stable atom using using classical physics. All right, it's just not going to happen. Now, classical physics is really important. It gets the spaceships in orbit around the thing. It gets people to the moon, gets satellites in orbits. It describes how Jupiter goes around the sun, stuff like that. However, classical physics was not working very well when it comes to chemistry. So a new theory was needed. So Bohr came right out and said, this isn't going to work, all right? So we need a new theory, and it's now called quantum or wave mechanics, depending on who you talk to. And in this new model, there was some really new kind of revolutionary ideas. And one is that electrons can only exist and are restricted to certain orbits. And they called them stationary or quantized energy states. And they were able to determine a model for how this works out. And the energy of these quantized states minus RHC over n squared. R is called the Rydberg constant. There's the value for it. You do not have to know that number, all right? I've already made you do H and C and Avogadro, stuff like that, but this is not one you have to know. It's helpful in this section, but it's nothing you have to know. But there's Planck's constant H, there's the speed of light C, and N is the quantum number. And quantum numbers are whole numbers that go from 1 up to infinity. And N of 1 is the closest to the nucleus you can get. And then N of 2 is a little further out, N of 3 is farther than that, etc., etc. And this was Bohr's model that he proposed, and he thought it was better than the current model was used. So it's worth talking about Bohr's thing here a little bit. And if you have electrons in quantized energy states, then the delta E, which is the change of the energy, can only have certain values. Now, we're going to start using delta a lot here in the Chem 221 series. Delta is always final minus initial. So, for example, if you had a delta temperature, it would be the final temperature minus the initial temperature. But here we're talking about delta energy, so it would be the final energy minus the initial energy. And in theory then, if this thing works, you could find the delta E for different electron transitions in something like hydrogen, which is cool. Now, n equals 1, as I said, is closest to the nucleus, and that's going to be called the ground state. So if there's no other external energies, the electron should be in the n equals 1 state. And those higher states, n equals 2, 3, 4, 5, 6, etc., those are all going to be the higher energy states. And from this, you can actually calculate the change in energy.
According to the Bohr model, when a hydrogen atom receives energy, its electron leaps from a low-energy orbit to a higher one, forming an excited state. As the atom loses energy, the electron jumps back to a lower-energy orbit, releasing light as it goes. When gaining energy, the orbit to which the electron jumps depends on the amount of energy involved. When the electron occupies the lowest energy orbit possible, the atom is said to be in the ground state.
So when the electron's at n equals 1, that's like the home base for the electron. Ground state is the better name for it. But anyway, sometimes it's like, boy, I want to travel. So the electron jumps to a higher state, 2, 3, 4. It takes some energy to do that. It doesn't happen by itself. But after a while, when the electron's at the higher state, it says, oh, I miss home. So it wants to go back to the home state, back to the ground state. That actually releases energy, and we'll talk about that here in a little bit. Notice that on the y-axis there, that's an energy axis. So if you go up, it takes energy. If you come back down, it actually then releases energy. On the right-hand side there, you can see the actual energies per electron in these different states. And you can calculate then the energies released, energies given off, if you want to, which is kind of cool. So let's calculate the energy, the change in energy for a mole of electrons falling, i.e. going back to home base, n equals 1 from n equals 2. So this electron earlier went up to n equals 2, but now it wants to go back to n equals 1 state. Now, along the way, we're going to use some constants, and they're listed there on the right. R is the Rydberg. You don't need to know that. But the other three, I'm hoping, do look familiar. Planck's constant H, speed of light C, and N sub A is the symbol for Avogadro's number, 6.022 times 10 to the 23rd. And remember that joules are the measure of energy. 1,000 joules equals 1 kilojoule. So when you do this, the energy of the individual states is minus RHC times 1 over n squared. But because we're doing it for a mole, I'm going to throw in Avogadro's number there as well, because we have Avogadro's number of photons. And when you factor out the minus RHC over RHCn values, then you have final minus initial, which is 1 over the final state minus 1 over the initial state. So when you go through the math, and I encourage you to check this out if you want to, notice how you're going to get 1 over 1 squared minus 1 over 2 squared. That's like 1 minus 1/4, all right, which is like 3/4. And it's going to be an overall negative term, and it comes out to be minus 984 kilojoules per mole. So this is actually a way to calculate the energy of an electron, a mole of electrons, going from 2 down to 1. We're going to see that anytime you go from a higher n to a lower n, the values will always be negative. And chemists call negative energies exothermic, which means that energy is released. And exothermic reactions give off energy. In this case, you might be able to see it or measure it, depending on where the wavelengths were and stuff like that. So pretty cool kind of stuff that Bohr figured out all on his own, more or less. However, I said earlier that you might be able to see the wavelengths. Now remember that our eyes only see visible wavelengths in the spectrum. They don't see all of them. So you can actually calculate from that minus 984 kilojoule per mole number, you can calculate the frequency nu and the wavelength lambda of this species. Now in minus 984 kilojoules per mole, there's a couple things you've got to do before you turn it into frequency and wavelength. You have to turn kilojoules per mole into joules per atom. Now there are 1,000 joules in a kilojoule, so we're going to multiply that number by 1,000 to get joules per mole. But we've got to get rid of the moles too. We want to have it per photon. So what that means is we're going to end up dividing that number by Avogadro's number. And from that, we're going to get the joules per photon. So in this part right here, first of all, I converted the kilojoules into joules. So you can see there's a 10 to the third. And then we're going to divide by Avogadro's number, which is so many, in this case, photons per mole. That would initially get us the energy per photon. But I'm actually going straight to frequency here. So frequency equals energy divided by Planck's constant. I'm also going to divide by Planck's constant here, and lo and behold, you end up with this number right here, which is the frequency. Now notice that really there's a negative right there, so it kind of looks like frequency should be negative, but usually what people do is they refer to frequencies and wavelengths as positive numbers. All right, it's totally fine to think of them as being always positive. Certain really high level things you can have negative frequencies and wavelengths, but it's not the convention. All right, so if you see a negative frequency or negative energy, just absolute value it, i.e. make it positive. So this is the frequency. And when you take the frequency and the speed of light, you can find the wavelength. So 2.998 times 10 to the 8th meters per second divided by the frequency, you end up with a wavelength in meters, but then I'm going to convert it into nanometers because that's what people do most of the time, 122 nanometers. So this part, there's a lot of math, and I do encourage you to go through it on your own to see if you can make all these things work, because if you do, you've got this stuff totally knocked down. And what's super cool about all this annoying math, I know it's kind of annoying, is that wow, Bohr's model worked incredibly well when based on the actual experiment values. Like the numbers came out very, very close to each other, which was cool. And no one had figured out where these crazy sharp line spectras were coming from. So this picture here on the lower right is kind of important. It shows, first of all, how the electron is in the ground state, n equals 1, and then it's excited, and it's excited to the n equals 2 level. And then after a while, the electron says, nope, I want to go back to my home base. It's going to go back to the ground state. I'd like you to look at the energies. Notice how to get from the ground state to the higher state, it's a positive 984 kilojoules. But what we calculated on the last slide is that going from the higher to the lower state, it's minus 984 kilojoules. And this is real common with energy. If one direction has a positive energy number, then the opposite direction would be negative. So going from low to high was a positive number. Going from high to low is a negative number. We'll come back to that topic in a future lecture. So a couple of terms which are kind of important for stuff we're going to start seeing are, the terms that are important are absorption, which is when energy is absorbed, and emission, which is when energy is being released. And absorption of energy, absorbed energy, is always going to have positive numbers. We're going to refer to those as endothermic. It takes energy to make it happen. Like that electron in the ground state isn't just going to go up to n equals 2 by itself. It's going to have to be prodded a little bit. So it's an endothermic reaction. It's going to take energy. It's going to have a positive delta E. On the other hand, the emission lines are energies going from higher n back to a lower n. In this case, n equals 2 to n equals 1. And they're always going to have negative numbers. So they will always be exothermic. So a lot of things in this slide. Exothermic means energy is given off. That's a negative energy. And all of the emission lines that we're talking about, all the sharp line spectra, those are all emission lines. On the other hand, endothermic are positive numbers. Those are absorption lines, and we'll talk about that more later. So here's a kind of question you might see. It says, which diagram below represents an emission line? Now, emission always means that energy is being given off, exothermic. Absorption is when energy is being absorbed and you have positive energy values. So as we talked about in the last slide, to have an emission line, you have to have an exothermic reaction and a negative delta E. And that means going from the higher to the lower end. So that's going to be diagram A, because A is going from n equals 4 to n equals 2, and that's going to give energy off. Now, diagram B would be an absorbance line or an endothermic reaction, because you're going from a lower end to a higher end, and it takes energy to go from lower to higher kind of values right there. So A would be considered emission, higher end to lower end, and that would be an exothermic energy. It would be a negative delta E. On the other hand, diagram B there shows lower to higher end. That would be absorbing energy to make that happen, or an absorbance line, and that would be an endothermic reaction. So in chemistry and in science in general, both emission and absorption, pretty important, all right? And in the lower right-hand corner there, you can see how you've got light going through a sample. There's some kind of slit. You can have both emission and absorbance lines be really helpful, and it just depends on the nature of what you're doing. Now in astronomy, they use a lot of times the measurement of emission lines in stars and faraway planets to identify the components of it, which is cool. But on the Earth especially, sometimes absorbance lines can be really cool. Notice here how the lines are kind of the opposite. So for hydrogen, which we're going to focus on in lab, the emission lines are just kind of like 4, more or less, lines in the emission labs. In absorbance of hydrogen spectrum, you'd see like black lines. That's where the light was absorbed, if you will, by the sample, and all the other light goes through. So they're both really helpful. If you go on in science, you'll definitely use, I'm sure, emission and absorbance in different kind of contexts, which is cool. But if nothing else, if you are using light bulbs to look around right now, if you have light bulbs overhead, those are emission lines, all right? Light bulbs are essentially an emission lines. You're exciting whatever gases are inside there to give off light so we can see. Pretty cool stuff. Now, why Bohr's model was so cool is that when they found those delta E values for those transitions between states, it was amazing how close the wavelengths corresponded with things like the Balmer series. So again, Balmer was the scientist who first discovered and measured the wavelengths, but he didn't understand what was happening. Well, Bohr's model knocked it down because he was able to get really great values for the wavelengths associated with these transitions. So when he calculated, for example, the n equals 6 to n equals 2 transition right there, it came out to be almost exactly 410.2 nanometers, which is really cool. Now there's other series of lines. So Lyman did some ultraviolet lines, and this guy Paschen did some infrared lines, similar to what Bohr did. But Bohr's model did a really great job in identifying where these came from. So they went from higher n values to lower n values. Those are all emission lines that are ones we see. So that was really a testament to his ability. He was the first one to kind of figure out the origin of these emission lines and where they came from, which is pretty cool. So Bohr is great. He got the Nobel Prize, and he deserved it. There's an element named after him, and he really started to introduce what are called quantum numbers, which we'll talk about in a little bit. But Bohr just kind of came out of left field, so his theory wasn't perfect. First of all, Bohr's theory worked great for hydrogen, which is what we're going to focus on in lab, and it also worked really great for the helium plus 1 ion. And both of those, hydrogen and helium plus 1, have only one electron in them. So if you only have one electron, it works great. But unfortunately, if you have more than one electron, Bohr's model didn't work out too well. And also, he introduced this idea of shells and quantum levels kind of just ad hoc, like out of the blue. There wasn't a reason for him. So Bohr's model definitely was a step in the right direction. But now we're going to go on to quantum theory, or wave mechanics, which is where they started to really get hardcore about how this stuff all works out. And these are the theories that have worked really well. But Bohr is pretty cool.